is the primary supercomputing center for DOE Office of Science. So what I'm going to talk about is how, as we move towards exascale, energy efficiency and really power consumption has become the primary limiting factor for the design of future machines. And it affects all of our hardware architecture moving forward, but it's also going to deeply affect our programming environments. Want to talk about, this is kind of the outline of the talk, is talk about how the programming model and the programming environment is really a reflection of the underlying machine architecture. And the machine architecture is evolving rapidly away from the design principles we use to design MPI and OpenMP and all the current programming environments. And so they're increasingly mismatched with our evolving exascale computing architecture. There's changes in computer architecture, trends and costs, and the consequences in the programmability of the systems. They're going to become very, very difficult to use unless we re-architect our software environment to match the emerging hardware trends. And it'll end with some recommendations of where to reformulate our programming models for the future of HPC with an emphasis on performance portability, because that's what we want. We'd like to have our code naturally perform well when you write it in the programming environment, and we'd like it to be transportable across different architectures in the same time frame, but also as you evolve forward to future machines, you'd like it to continue to perform well, and we refer to that as performance portability. So this is a chart that we put together. There was a meeting that DOE held in 2009 that involved a lot of the different vendors to talk about the future trends in hardware architecture. I'm kind of surprised that even though we kind of did this by the seat of our pants at the time, that these trends have actually starting to get realized. And you'll notice the key thing here is that the dramatic increase in the power consumption anticipated for these machines. But even with that, we're unable to achieve performance improvements through clock frequency increases anymore. So you're seeing this dramatic increase in the parallelism within the node and across the machine in order to achieve continued performance increase in the future. And that's scary. But the other thing we're seeing is pressure on memory bandwidth and memory capacity, which pushes us towards strong scaling, which is very, very difficult for parallel programming. The goal for programmers at all levels, so these dramatic shifts are scary enough just if you look at it in the face, 1 billion way parallel machines. But the programmers, we think of them as sticks in the mud. They only want to program in Fortran. But we actually talked to some of the weapons designers from the NNSA and also the scientists from SC office, and they said actually they understand they need to rewrite their codes. They're willing to rewrite them from scratch. And when they rewrite it, though, they would first off, they want to do this only once. They don't want to do it every 3 years. But the second thing is that when they do it, they'd like it to be such that they minimize the number of lines of code they need to change when the next generation machine comes out. And right now, the evidence that our current programming environments are broken is that you have to almost completely rewrite your code to move from a GPU architecture to a CPU architecture. And even when the next generation GPU comes out, you have to rewrite a heck of a lot of code in order for it to continue to perform. So performance portability is about minimizing the number of lines of codes I have to change when each new machine comes out, and the target then is the first derivative of technology changes. That means you should look at what's changing the fastest as we move forward. It used to be clock frequency was the thing changing the fastest. The thing that's changing exponentially now is the number of processing elements in the machine. So we need to come up with programming models that are actually insensitive to the number of cores. MPI, we have to actually know your rank, 0 to 1,000 or whatever, your thread rank. When we go to 1 billion, this seems like a crazy thing to do. So, you'd like a programming model that abstracts away the notion of the number of cores. You need it to be less sensitive to sources of heterogeneity in performance or non-uniformity, because that's something we expect to increase in the future with power throttling. You need to have something that can handle smaller memory capacities, and also the most important thing is understanding data movement constraints. And we want these to be durable abstractions. We refer to these as our abstract machine model for hiding and mitigating these effects. So, to get into this, we should talk about what is an abstract machine model, because, the abstract machine model is very important to a programmer. The abstract machine model represents what attributes of the machine are important for me to reason about how to get good performance. And there can't be, I can't have too many of those things, bouncing around in my head at the same time. We want, when you have to have some conception of the machine in your mind to enable you to reason about how your algorithm, how your code is going to map on to these supercomputers, and also have some rough guess about what's the right thing to do to get, power, energy efficiency, and performance for, different algorithm and execution model choices. These machines are exceedingly complex. Our current abstract machine model, though, is very simple. It identifies which of those many different things I, as a programmer, need to reason about. And just to give you an example, a historical view of this, when we had SMPs, the SMP model, it was not exactly true, but it was true enough that processors could be considered equidistant to each other. And also processors could be considered equidistant to the memory that they accessed. So this was kind of the classical SMP model. We call it the PRAM model. And so, there's no notion of there's everything, when all the memory is equidistant, then you can, just say here that I lay stuff out in memory with these multi-dimensional arrays, and I just hand out loop iterations to the different processors. So that's our old school SMP model. As we move to clusters, though, we could no longer hide the fact that the distance between the memory and a neighboring processor is far greater than the distance to my local memory. So eventually we, split from the old PRAM model, and we had an MPI model with distributed memory. So you have your local memory becomes explicit, and then you send messages between the processors. And that's a new abstract machine model. MPI, the way I program a machine, when I think I'm targeting MPI, I'm programming a machine that the cost of sending a message to a neighbor is way more than the cost of accessing my local memory. Kind of a optimization of this is partitioned global address space, but still it has a very strong notion. It's targeting the same machine model, but it has a very strong notion of local memory versus non-local memory. And so now we're entering this era where we don't know what the new abstract machine model is, and this is just don't worry too much about this. We have hierarchical memory spaces. You have your GPU accelerator memory, which is fast. You have the slower memory in the host. We're uncertain of the communication fabric. Well, what we need to do is figure out how to reason about this new emerging model. So if we think about all the design choices that computer architects have to make in order to design the next generation machine, these are all the elements that are potentially players, potentially important for performance as we formulate our next generation machine model. And this list is way the hell too big. So this is our system, this is our node, this is a processor core, and these are all the design choices that you have to work through. Now, mere mortal can't reason about these things. What we really need to figure out is, for each of those parameterized machine attributes, is it designed in such a way that I can, it may have an effect on performance, but it's possible the effect is small enough that it's reasonable for me to ignore it. So that's the first, aspect of this. Find out what attributes of the machine model are reasonable to ignore. The next level down is, whether to abstract it or virtualize it. And that's a case where how to lay out or map your algorithm onto the machine is well enough understood that I could automate it. I could expect a compiler or a library to actually automate that process for me. And again, it takes it off the table for the programmer to worry about. The thing that's very interesting moving forward, though, is figuring out what kinds of things a programmer needs to expose or express in order to enable the rest of the framework to automate data layout. And these are places where we need to make our programming model more expressive. And an example of this that I'm going to talk about for most of the rest of this talk is data locality. Right now, our programming models are using this old school view that everything is equidistant. And as a result, we didn't ask the programmer to express information about data locality. But in the future, going forward, if data locality is the most crucial thing for achieving performance and energy efficiency, then that is something that is a fundamental change in our programming environment that we need to ask the programmer to express information about that, because if we don't, there isn't any automated way to do it for you. Okay? So, we want this model to be as simple as possible, but we don't want it to neglect things that are crucial for reasoning about performance. So let's talk about data movement. I forgot to drop in a slide about the problem with wires, but I'll just give you the background. The problem with wires is that the cost of moving data on a wire is proportional to the distance that the wires travel. The equation is basically power is equal to bit rate multiplied by distance traveled divided by the cross-section area of the wire. This gets it really interesting when we think about chip architecture. We're talking about optics to link cabinets together, so let's take that off the table. When we're looking at what happens on a chip, we've still got wires on the silicon to carry data around. This equation, power, bit rate times distance divided by cross-section area, means that when you shrink down the wires on the chip together to the transistors are actually still improving in their energy efficiency, but the wires are not. So as you shrink those things down, you see here that the cost of performing a floating point operation is improving with each generation of chip technology. Not as fast as it used to, but it's still improving. But the cost of moving data across the chip is not. So we're getting to the point now that the cost of moving data 5 millimeters across a chip, and we're talking about like these NVIDIA GPUs are 500 millimeter square chips, right? That cost of just moving a very small distance in the chip is going to exceed the cost of performing a flop on it. Our entire programming model is based around conserving flops. Everybody talks about sustain to peak, peak flop rates, yada, yada, yada. And yet the thing that's the most important to worry about is data movement and data locality. We've got it, everything is upside down the way that we program machines today, and we've got to get over it. The second thing is that the cost of going off chip is enormous. And the gap between the cost of going off chip and the cost of performing a flop on chip, this being an exponential scale, is increasingly important. And as bandwidth gets constrained in future machines, you need to be more careful about managing when data is on or off the chip. So, as we scale out architectures in the future, what we're looking at is a chip architecture where, we have to increase cores at an exponential rate. And, you can have 3D chip stacking for memory, but for your processor cores, it's going to scale out in 2 dimensions. And the consequence of that is that you need to understand the cost of speaking between cores that are close to each other on these chips in the future is a lot less costly than this core speaking to a core at the far end of the chip. Our programming environment offers zero ability to express anything about this, and there is no hero compiler that can do this automatically for you. So we're really kind of screwed right now unless we rewrite the way we program these things. So this is the way that we like to reason about this. Vertical data locality management is managing the movement of data from memory up through the cache hierarchy to the processing elements and back down again through the hierarchy. And as I mentioned, there's like a 3 order of magnitude cost if you have to go off chip for an access. So in the past we've depended on automatic caches in order to automate, enable it to abstract away the notion of off-chip versus on-chip memory. So an automatic cache, it basically says, don't you worry about, whether something's off-chip or not. If you use it pretty data that I pulled onto the chip pretty recently, I'll make sure it's there for you. It's gotten to the point now that this is not a reasonable approach. And scratchpad memories enable you to be explicit about I know that the data is on chip. I'm going to access it when it's on chip. And now I know that I'm going to move the data off chip explicitly. So that's a case where it's something that we've abstracted in the past, but as we move forward, we probably need to have more explicit control of it. So rather than abstract it, we should actually make our programming environment more expressive. And that's the case with CUDA copy, moving stuff on and off fast memory, and the accelerator is kind of in that vein. And then we have horizontal data locality management, and that's understanding communication between peer processes on a parallel, or threads on a parallel machine architecture. And so horizontal data locality management is understanding reasoning about topology, whereas vertical data locality management is reasoning about spatiotemporal optimization. So our old mental model, reduce flops. Because it used to be in the old machines that flops were the most expensive part of the machine, and so we're always worried about conserving that flop. With the new technology trends, the cost of the flop is cheap. It's not free, but it's kind of gone from high-end flop to IKEA flops, or that was for a European audience, so it'd be Walmart flops here, I guess. And so new costs center around that horizontal and data locality management. So you'd best find a way to worry about conserving data movement and not conserving flops. So, among the approaches that are on the table now are communication avoiding algorithms, so reformulating. So this gets back to our abstract machine model. If you're worried about minimizing data movement, then you need to design algorithms that minimize data movement. All of our algorithms are designed to reduce the number of flops you have to consume. So, for example, FFT minimizes flops, but it has this ginormous butterfly transform that we have traded data movement in order to reduce the flops. If data movement is the thing you're worried about, the FFT is really not such a great idea. and so you need to reformulate your algorithms to minimize the amount of data movement, potentially. We also have more expressive type systems that are able to express multi-dimensional layouts on the machines, and also potentially return to functional semantics, where the data locality is implicit in the design of in the coding. So right now it's a real pain in the butt to do CUDA copies because you have to be explicit about expressing which arrays you're moving, which you're not. If you go to old functional programming paradigms, that becomes implicit, and it's something that you virtualize that we currently have that's explicit in the programming model for GPUs, but we could make it virtualized if you went to a different programming paradigm. So I'll talk a little bit about some software mechanisms for expressing locality. We already talked about the current models that we have are kind of an equidistant, a PRAM model. So if you think about OpenMP, it basically says that all memory is equidistant to the processors, which is an old school view of an SMP node. And so at that level, it's a PRAM model. And then the next level up is MPI, where we assume all the processes that I'm sending messages between, that those are also equidistant. That was true at the time that we originally created OpenMP and MPI. It is no longer true, and it'll be increasingly untrue as we move forward. The problem is that the machine used to be pretty flat at those two levels, but it isn't. What's wrong with flat? We'll skip the what's wrong with flat MPI. I think everybody here believes that. But what's wrong with MPI plus X? It's good because it recognizes the biggest cost delta is when I go off chip and have to send a message to my neighbor. But it's not good from the standpoint that the cost of sending to a node that's the distant end of, say, a torus interconnect is far more than the cost of sending to a local node. And the same goes for OpenMP within the chip, that the cost of sending to a NUMA domain that's distant is far worse than sending it to a neighboring processor. So, the abstractions that we have do not properly capture the performance. We need a new hierarchical abstraction. Here's an example that, two-level parallelism is a good thing. So for 3D FFT, if I go OpenMP plus MPI, I get a performance boost over just doing flat MPI. So that's a good thing. So that's the benefits of at least capturing that two-level locality. But then when we look at OpenMP plus MPI hybrid on new NUMA nodes, so this is it has 4 NUMA domains. This is the latest Cray XE6 system. We get improvement, and then we cross a NUMA domain, and it's actually slower than if we hadn't parallelized the code at all. And this is because we are pretending with OpenMP that all the processors on a node are equidistant, but it's no longer true. It's bad enough that we aren't seeing the kinds of speed-ups that we should expect from intranode parallelization with OpenMP, but it's worse if you try to do an AMR code where data affinity is a lot more complicated. This is just for a simple case here. So it's, I call this a revenge of the SGI Origin 2000. So what used to be true for system-wide cache coherence is now true even within the node, and the lessons that we learned a decade ago in the Origin 2000 are re-emerging now as we try to reformulate OpenMP. So now PGAS Languages program, this is Partition Global Address Space. They offer a better abstraction than MPI that explicitly understands 2 categories of memory, that everything I can do a load store to memory on somebody else's node or memory in my local node. It's way more convenient than having to go to package up messages when I communicate remotely and do load stores when I'm doing local. And it understands 2 different categories of memory, memory that's local to me and memory that is not local. So that's good. And it enables you to have powerful locality-aware programming constructs. So for example, after you describe a data that's laid out across the machine, and you know what part of that data array is local and what part isn't, you can create a for-all loop that will automatically execute the iterations of that loop where that data array is local, and it'll automatically know not to execute the iterations of the loop where the data array isn't. This is a very powerful construct. It says that I just say how the data is laid out across the machine, and automatically it'll execute, all the execution will happen where data is local. Fantastic. It's better than a flat model, a PRAM model, but the problem is that the machine, of course, isn't flat. It's more hierarchical. So local and not local may be insufficient to describe the true nature of the machine. So what we really want to do, and so if you think about a UPC as a model, this is a construct for describing how data is laid out on the machine here. So we have our, 3-dimensional array for block structured grid in 3D, and UPC allows me to say, lay out this data, partition this and hand a different slice of this 3D block across all the processors in the machine. And when I do that for loop, the execution will automatically be bound to where that data block is local. If you want to do a 3D domain decomposition, though, it doesn't have a way of describing blocks, that a multi-dimensional decomposition of the blocks. And as a result, you have to do this really kind of back-asswards way of expressing 3D domain decomposition. So the programming model is more expressive than OpenMP and MPI, but it's not expressive enough. So maybe you should have, a construct that says I can do like a 2-dimensional blocking factor. And the problem with that is it's not really matching the target of our machine target. This 2-dimensional layout allows me to express 2 layers of domain decomposition, but doesn't express information about topology. And, topology is important for managing our horizontal data locality. So perhaps what we should come up with are hierarchical data layout statements. And there's a number of people working in this area. So David Padua at University of Illinois has HTA, which is hierarchical tiled arrays. They have the Chapel people working on this. They have the array building blocks. The notion here is that I want to express different 3-dimensional tilings of data arrays. So if I have a multi-dimensional array, I should also be able to express a multi-dimensional partitioning of said array. So I'd like to be able to naturally move from the global iterations index space of an array, the natural way that I like to think about my problem. I have a giant it's a fluid dynamics simulation, and I have the overall three-dimensional domain for that array, and I want to be able to express how to break that overall domain into smaller parallel pieces. But more importantly, I'd like to preserve that UPC for all construct where I describe how the data array is laid out, and then I have a loop with some operation on it, and I want that for all to execute locally where the data is local. So to do this, you can build up a description of a hierarchical tiling or a hierarchical layout where I have, the blocking within the node, so I express the topology within the node, and then I also have a blocking factor for describing how the problem is partitioned across the nodes of the machine. And then when I hit this looping construct that is a triply nested loop that walks through all of those data arrays and does a stencil computation, I don't have to change it. Even if the layout of the machine, the layout of the problem of the machine completely changes, I only have to express that in one place, and that's where I allocated the array. For all of the other 1,000 loops that I have in my code, I don't have to change a single thing. These loops automatically will operate where the data happens to be local. And that's hugely powerful because it says that I only need to change 3 lines of code when I move from one machine to another. And all the other 750,000 lines of code, I don't need to change. It automatically executes where the data is local. And that could be hugely powerful. So that's one of the major ways that things will change in the future. So, conclusions in data layout is that, failure to express hierarchical, multidimensional data locality has a substantial cost for application performance. And there's no way with the information that current programming models provide to our compilers, there's no way they can figure it out for themselves. It's just, there's not a heroic compiler that's going to dig you out of this hole. So what that means is that we need to offer programmers a way to express information about the 3D layout of their problem, and these hierarchical data layout statements are one of the most promising ways to offer that kind of expressiveness. And then after you express information about data locality and tiling, it enables the compiler to automate most of the rest of the process of breaking up the problem into discrete pieces. And also, more importantly, it enables the runtime to reason about how to lay out the problem on a very complicated machine architecture that changes each generation. So the data-centric parallel expressions offer better virtualization of processes and threads as well. I say that I'm laying out my problem in 3D in the machine. I don't need to know how many billion threads there are, which is, with OpenMP, I know threads 0 through N. With MPI, I have threads 1 through N or whatever. If I say, this is how I want to lay out my problem on the machine, and then if there's a thread there, it'll execute in the data that's local, then that enables me to hide the fact that there's a billion threads in the system in these future exascale machines. And that is also hugely powerful and a huge departure from what we currently do. So let's talk also briefly about interconnects. So, technology trends there and their effects on application performance. The issue with scalable interconnects is that in the past we've built these fully connected networks where everything's connected to everything with full bisection. But the number of wires that you need to wire up a machine like that is prohibitively expensive. And so people have been looking at hypercubes, toruses. There's also high radix, dragonfly type networks and stuff as well. But the key is that people are trying to figure out how to economize in the number of wires in the system. So that means that in some cases we're seeing very constrained communication topologies. You have bandwidth taper in the upper tiers of fat tree type networks, or you have torus type networks that have a very low topological degree. But the good news is that if you actually examine application codes and their communication patterns, this is kind of a heat map which says that processor X here is speaking to processor Y, and it lights it up if they're actually speaking to each other a lot. And if you take a look at this large mix of codes here, the number of communicating partners is actually pretty low. So that's a huge opportunity here. It says that a full bisection bandwidth network is a huge waste, because all those black tiles there are places where I've got a wire and I'm not using it. So you know, huge cost waste if you build a machine that's got a full bisection bandwidth is what this says. So great, opportunity. You know, we can do toruses, we can do hypercubes. Now the problem is that none of these communication patterns has a one-to-one mapping to any of the known topologies that we were talking about. They do not map directly to a torus. They do not map directly to a hypercube. And graph embedding is an NP hard problem. So you have to do something more. You either have to have some intelligent, a way to intelligently lay out your tasks on the system, but the current way that we use MPI and the current way we write scheduling systems, they don't offer us any opportunity to do that. Schedulers are dumb. They choose the first n processors in the system they can find and schedule your job there. Likewise, maybe we could explore adaptive topology. So we did a project called HFAS, which used optical circuit switches to automatically rewire machines. And so maybe there's something with adaptive topology, but current networks don't do that. So there's an opportunity here. It's just how do we exploit that? So let's take a look at like jobs running on our most recent Cray machine that has a 3D torus on it. And one of the things we saw here was a huge amount of job variability. When we actually examined how the job was laid out on the machine, what we found was that, you know, right after you rebooted the machine, you'd get a relatively contiguous piece of the torus in the machine. And when the job got a compact piece of the machine, it executes very fast. But over time, as jobs are scheduled and retired from the machine, you start to get fragmentation of the torus. And so the greedy scheduler, as we get more fragmentation, we grab the next n processors, we get this huge slowdown. So what we're seeing here is we had an opportunity here to have a MPI express something about topology and have a job scheduler that takes that information and uses it to schedule a job, so it uses compact regions of the machines. But in fact, we don't use MPI, we don't have a facility to express information about topology, and all of our schedulers are stupid, and they don't allow us to exploit that information, even if we had it, to schedule jobs compactly in the machine. And the result is a huge waste of hardware resources, a huge waste of power, a huge slowdown of performance. And this is topology optimization. So, you know, as I said, topology embedding is an NP hard problem, but we came up with a method called fit trees that turns it into, it's a heuristic that makes this, enables you to do a pretty good layout in polynomial time. So it's not an NP hard problem, which is a huge benefit. And the idea is that you imagine a virtual machine that's got a fat tree, a full bisection fat tree interconnect. And we just start blowing away links. Whoops. We start removing links from different layers of the fat tree if they're unused. And also pushing the pieces that communicate frequently with each other. We sort the network and we push them down to the leaves, so that areas that have high communication of intensity get packaged close to each other at the lower part of the fat tree, and things that are communicating less frequently go to the upper parts of the fat tree. So after we've removed all possible links that you can remove without affecting job performance, the resulting tree here is we call a fit tree. And if you look at this graph here, this is for a wide variety of codes that represent the DOE Office of Science workload. You can see that this is a multi-level, you know, fat tree that we've made into a fit tree. And it shows that you can blow away a huge number, up to 80% of the switches in the upper tiers of a fat tree, if you had some information about the communication topology of the code. And we don't. But this is the opportunity provided to hardware designers, switch manufacturers. If the programming environments, the programming models people step up to the plate and enable programmers to express this information, this is how much you could reduce the cost of your interconnection network for future machines. And it's substantial. And so this is an opportunity that's still on the table that we're unable to exploit. So there's a huge opportunity for communication topology optimization to improve performance. Runtime information gathering for active task migration or using circuit switching to rewire machines. Either case, you have to express information about your communication topology in order to exploit these ideas. And we don't allow our programmers to express that. And so big opportunity that we're wasting. So need to provide the compiler, runtime, and resource manager with information about job topology requirements. So heterogeneity and inhomogeneity and its effect on asynchronous programming models. So one of the things that has come up too is that we're starting to see heterogeneous computing, where you have hybrid CPU, GPU computing, or if you're in the Intel universe, you have little cores and fat cores. So that's the first order of heterogeneity, and some people say, well, the correct answer is just don't do it. Well, you can do that, but there's a lot worse things coming. We of course have irregular algorithms, so even if you decide to use homogeneous computing, you got the best opportunity for improving performance and reducing memory consumption is to use adaptive algorithms like adaptive mesh refinement, which only apply computing where it's needed, or sparse matrices and stuff. We also have increased use of fine-grained power management, which makes, even if you have homogeneous cores in the machine, they start to look pretty heterogeneous when they're power throttling up and down. In fact, Sandy Bridge, it has thermal throttling, meaning when the chip heats up, it'll automatically dial back its performance based on how hot it is, and depending on which bin you get your chips from, they will get hot at a different rate. So you have thermal throttling is going to make things be non-deterministic in terms of clock rate. There's non-uniformities in the process technology that's going to make these future chip multiprocessors non-uniform in performance. And then also fault resilience. There's a discussion about having software recovery from transient failures. Well, ECC even is not instantaneous. So imagine if you have software handlers to recover from errors, you have a huge source of inhomogeneity that's unanticipated inhomogeneity. And this is an example from 5 years ago where we had a job executing on a XT4 system, and these little spikes here, we were trying to figure out what they were. We thought they were OS noise. We thought maybe it was our algorithm. Turns out these were ECC errors that in the memory system, but they were recoverable ECC errors. But it turns out there's a cost to recovering from an ECC error, and it was causing our job performance to really tank because of that. Now, these spikes will be much higher if we start to have software-based resilience, which is something we're moving towards. So, whether or not you have a homogeneous machine or not, it's going to look heterogeneous. Forget about accelerators. So maybe you're not keen on using GPU-accelerated machines. Even using a CPU-based machine, everything's going to be executing at different rates. Under that circumstance, our current bulk synchronous programming models, where everybody's doing roughly the same thing, are not up to the task of running efficiently when we have performance variation or jitter across the machine, like we're anticipating. And this means that we need to think of new programming models, new execution models that are not SPMD, not SIMD type models. There's a lot of talk about going back to asynchronous execution models, classic coarse-grained data flow. We have Swarm, HPX, and other concepts that arose in the 1980s and then disappeared. They're all starting to reemerge because the only way to deal with performance heterogeneity is not to try to quiesce it. In fact, is to try to turn around and embrace it and develop a way of running your code, running jobs so that they can actually execute asynchronously in the machines. So why wait for Exascale? Everything's breaking now. I told you about all of these things that are coming. People say, well, we don't know what the Exascale machine looks like, so we can't really start rewriting our programming environment. And what I'd like to say to that is bull. This is our last two machines that we purchased at NERSC, XT4, and then we have NERSC 5, which is an XE6. Thing to look at here is they're approximately the same total amount of investment. When you throw $50 million at a machine, you end up starting at approximately the same part of the top 500 list. Top 500 is not a measure of performance, it's a measure of how much you invested in the machine, really. So we went from 4 cores to 24 cores per node, even though the total number of nodes in the system is equal or even went down slightly between those two systems. So this is exactly what we're predicting as we move towards exascale, is the exponential increase in cores per node, but probably relatively flat increase in the number of nodes in the system. The clock rates have gone down. The number of NUMA domains, non-uniformity even within the node, has gone up. We went from 1 NUMA domain to 4. Our next generation machine will have 8. And we're also seeing less memory per core. We're seeing more memory per node, but if you try to think in a per core basis, it's going down. Everything that we're saying, when we talk about the roadmap to exascale and being a billion-way parallel and all of this, we are at the beginning of this exponential growth curve, and we're exactly on track to what we predicted back in the 2006 DARPA report, and then we re-examined it in 2009. It's happening now. Everything you need to know about what's going to be hard about programming an exascale machine is already apparent and is already underway today. So why wait? Focus on the important things. Don't imagine what the exascale machine could look like. We already see what is going to happen. Focus on the design trends. And the future programming environment should focus on mitigating these design trends, what I call the first derivative of change. Performance portability is the correct metric, not peak flops, not sustained to peak. Performance portability. I want my programmers to be able to minimize the number of lines of code they need to change when I go from generation 1 of a machine to generation 2 to generation 3. That is the correct metric. And when we want to do a sensitivity analysis and extrapolate out, and to this end, we should concentrate on the hardware extractions that correctly minimize the impact of the design trends. And the design trends are increased cost if you ignore data locality. The design trends are exponential increase in parallelism. And those are the things that we're trying to mitigate as we move forward. So the programming model is and should be a proper reflection of the underlying machine architecture. The programming model as it is now is no longer reflecting what the underlying machine looks like, and that's why everything's breaking. So we need to reconsider what aspects of the machine we can ignore, what we can abstract, and what we need to expose. And the change is that we need to abstract things like the number of cores, which we currently expose, and we need to expose things like data locality, which we currently ignore. And so this is kind of like the conclusions and, data layout. We want to make data layout more expressive. So currently we ignore it. We should expose it. Horizontal data locality management, we should virtualize it, but we should do it by having more expressive data layouts. The vertical data locality management, make it more expressive. For heterogeneity, if we go to an asynchronous paradigm for execution models, we can successfully virtualize that. And for parallelism, we currently put it in your face with MPI. We should find a way to virtualize that. I'm just going to go quickly through some bonus slides since everybody's talking about I/O here. I'd also like to point out that currently we're trying to scale up POSIX shared file systems, and we do POSIX shared file systems because disk reliability's kind of gone down, so you like to consolidate that. The problem is that we have POSIX semantics, and POSIX semantics are like scaling up cache coherency on a block device to span the entire machine. And we also have imperative control of file layout, which makes it hard for the I/O system to choose alternative data layouts. And maintaining consistency for metadata servers is increasingly a serial bottleneck. This is a terrible path forward. And so the relaxed POSIX, the problem with that is we've talked about it for 20 years now, and still nobody knows really what it means, and you can't explain it to an applications programmer. So give up, Dorothy. It's a bad idea. If you can't explain it to your apps people, and we've talked about it for this long, it's not the correct way to think about it. I think that the most interesting way to think about it is object databases, where it provides a much better abstraction to hide relaxed POSIX semantics. So don't throw relaxed POSIX semantics directly at your users. Offer them an abstraction that allows your I/O system to implement relaxed POSIX semantics and not directly expose it to the user. And so you can use functional or transactional semantics to operate on your data objects. So if you go to an object database type file system approach, then you can use transactions to operate on objects where the data happens to be local. That enables you to embed more computing right next to your storage, which is something that's really difficult to do with our current imperative programming models. And you also need to have a semantics for affine remappings of disk layout and memory layout. So, I think Brent Gorda is going to talk about this. Wham Cloud has some really cool ideas in this area. We have HDF5 is an API that allows you to express object database type semantics, and even with conventional file systems, HDF5 allows you to express this tree-like hierarchy of objects for a system, and having this abstraction enables you to completely change the data layout on disk in order to get better block buffer locality or affinity. So if you're trying to use SSD caches and stuff like that, you can completely reorganize the data layout on your final persistent storage device, and the user never knows anything about it. And that's because object database is a better abstraction for hiding getting rid of POSIX semantics and going towards a relaxed POSIX relaxed consistency model that we've all said is crucial for being able to scale up file systems in the future. So check out Brent's talk. I think you'll have something interesting to say about that. All right, that's it. So any questions?